So this lecture is going to be on radioactivity and half-life. Let's take a look at our objectives. Everything in yellow so far we have covered, and today's focus is really going to be on objective 4, can discuss different types of radioactive decay and solve problems related to half-life. We are in fact going to try to cover all of these bullet points in the lecture today. So let's go ahead and get started. For your warm-up, I would like you to remind yourself what are the advantages and disadvantages to using nuclear fission in a power plant. Pause the video here, brainstorm your list, and check back in. So here's a reminder of the advantages, things like being climate friendly, not emitting carbon. We have large reserves of it. It remains constantly on, unlike solar or wind when, if the sun's gone or the wind's gone, we don't have power. And it's relatively cheap once you build this power plant. But some disadvantages, of course, it is non-renewable in the very long term. But moreover, it creates nuclear waste. And when we talk about nuclear waste, we're talking radioactive waste. And so we need to store that waste for a certain number of years until it becomes safe. And also thinking about the radioactive byproducts becoming very dangerous in case there was a meltdown like you might have heard of in Chernobyl or Fukushima, where that radioactive waste gets out and gets people very sick. So we're really focused on better understanding those disadvantages around nuclear waste being radioactive in today's lecture. So when you think about radioactivity, probably some images that come to mind are this radioactive symbol, kind of the classic yellow and black symbol. You might have known that Marie Curie actually worked a lot of her life with radioactive substances, but this was before we truly understood how harmful it was. She ended up dying of radioactive poisoning. You might think about like glowing green substances, which often you see in cartoons, not so much reality. And you might have heard of the Fukushima disaster or the Chernobyl disaster, where there were nuclear plant meltdowns and a lot of radiation was released into the public. So in today's lecture, we are going to focus on these 4 questions. What exactly is radioactivity? What are the different types of radioactivity? What are the effects of radioactivity on humans? And how long does a substance remain radioactive, which would relate to how long we would have to store the substance. So let's begin with, what is radioactivity? Radioactivity, when you have a radioactive isotope, remember an isotope is simply changing around the number of neutrons. If you have a radioactive isotope, that means that its nucleus is unstable. And kind of along the theme of everything we've learned in physics, nature really wants to get back to a stable state. And so what happens is this unstable nucleus is going to release particles from its nucleus in order to stabilize itself. And I really like this graphic here. You have the number of protons, or Z, on the x-axis, the number of neutrons, or N, on the y-axis. And you can see that there's this line of stability happening. The black here is the stable nuclei. And any yellow here is an unstable nuclide. And so the unstable yellow wants to get back to that stable black. And remember, when we're talking about stability of a nucleus, we're really referring to the electrostatic force, which would want to have the protons repelling protons. And then, of course, the strong force, which overcomes that electrostatic repulsion. That strong force is between protons and neutrons attracting to each other. So that attraction really holds that nucleus together. So as you can see, the number of neutrons here becomes really important to increase that strong force to the ideal amount so that the repulsion from the electrostatic force and attraction from the strong force are balanced, making our nucleus stable. So that's really all radioactivity is taking an unstable isotope and releasing some particles in order to stabilize it. Now, there are some different types of radioactivity that we're going to talk about. We're going to focus on 4 different types of radioactivity. The first one is going to be alpha decay. This is when you have that unstable nucleus, and it's going to emit a particle, but that particle that's getting emitted is going to have the same configuration as a helium nucleus. This guy over here, helium-42. We often refer to helium-42 as an alpha particle. That's why this is called alpha decay. You can write alpha, which would imply that there is a 4-2 configuration. Again, alpha is just a fancy name for the same thing as helium-42. So some examples of alpha decay would be uranium, uranium-238, releasing an alpha particle and becoming thorium-234. Or thorium-234 releasing an alpha particle in order to become radium-230. Each time it's releasing that alpha particle, that nucleus is just trying to get more and more stable. You can see that playing out right here. This was our first example, alpha decay of 238 nucleus. The decay event sends off that alpha particle and creates a daughter nucleus that is more stable than the parent nucleus. So this is alpha decay, when we're emitting that particle that looks like a helium-42 nucleus. Our second type of decay is going to be beta decay. You can see there's actually 2 types of beta decay. There's beta negative and beta positive decay. Beta negative decay. This is when an unstable nuclide is going to emit a particle of the same configuration as an electron. Sometimes we write an electron as beta negative. This is implying a 0, -1 configuration. Beta negative and an electron are really the same thing. Again, the whole point here is for that nucleus to emit a particle so that it can become more stable. Now, this is going to be a little bit strange, but for now I want you to know that an electron anti-neutrino comes along for the ride. Now, this is weird. We have not seen neutrinos yet. We haven't seen antimatter yet. We're going to get there in just a few days. So this will make a lot more sense as to why that particle comes along for the ride. But for now, I need you to know you should always write an electron anti-neutrino when involving beta negative decay. This symbol here looks a lot like a V. It's actually a Greek letter. When I write it, it looks like a more squiggly V. In Greek, this is pronounced nu. I know, kind of weird. It's called an electron anti-neutrino, so it has a little sub-E. And what you'll learn soon is that the anti part of this is the line over the top. So again, for right now, you just need to know that it comes along for the ride. We'll better understand why in a few days. A few examples of beta negative decay. Here we have iodine 131. That's going to undergo beta decay, releasing that electron or beta negative, an anti-electron neutrino, and xenon. Or thorium-234 undergoing beta decay. Again, we see that beta negative particle, an electron, and the electron anti-neutrino. What this looks like is something like this. What they haven't shown here is that that anti-electron neutrino is also released. So this is beta negative decay. The other type of beta decay is beta positive decay. This is when you have an unstable nuclide and it is going to emit a particle with the same configuration as a positron. A positron is pretty strange. A positron is actually the antimatter of an electron. It's the same as an electron, but opposite in every possible way. Kind of weird. We haven't covered antimatter yet, but we're going to get there in a few days. For now, when you hear positron, you should be thinking like an electron, but opposite. So it has a positive 1 charge. Side note, you may be thinking, positive 1 charge, it must be a proton. Nope, this is an electron with having all the same properties, but opposite in every way. We call this positron, it's also known as a beta positive particle. 0, positive 1 is the configuration coming along for the ride. And every beta positive decay has an electron neutrino, written as nu sub e, no line over the top, because that line before indicated an anti-neutrino. Some examples here, we have carbon undergoing beta positive decay. We see that positron and electron neutrino emitted. And it comes down to boron 11. It becomes a more stable nucleus. We also have sodium undergoing beta decay, beta positive decay, to become neon. And our last type of decay here is gamma decay. Now, gamma rays, we've kind of already learned about them. They might remind you of the electromagnetic spectrum. They're very, very energetic. And really, all that it is are high energy photons. We even use the same symbol as a photon. We use that gamma. Now, this type of decay often happens in conjunction with alpha or beta decay. So usually alpha or beta decay occurs and leaves the daughter nucleus in an excited state. And that nucleus wants to stabilize itself by getting rid of the excess energy. And so it pushes out a photon. It pushes out that gamma particle. You can see that here in the example. We start with cobalt-60. It undergoes beta negative decay to become nickel-60 and gets rid of some energy by releasing a photon. Now that nickel-60 is still highly energetic, so it's going to undergo gamma decay again. Once again, it pushes out that energetic photon to get rid of that energy, stabilize itself down into a lower energy state. So to sum up, we have 4 types of radiation that we're focused on: alpha, beta negative, beta positive, and gamma. Again, a few of these things are a bit strange to us, such as electron antineutrinos, electron neutrinos, and what exactly a positron is. We will come back to that in a few days, so for now, set those questions aside. We will get there. Now remember, all of this simply comes down to stability. Our radioactive isotopes are pushing out particles as a way of getting to a more stable isotope. In this particular graph, again, we have the proton number on the x-axis and the neutron number on the y-axis. And what's shown in yellow here is that zone of stability. That's where all of our isotopes want to get to. Now, if you're a beta positive emitter, you are going to be pushing out a beta positive particle. That's a 0 + 1 configuration. Now remember, as that happens, that means that we still need to balance our equations. That means that the daughter particle, the daughter atom, is going to have 1 less proton. So for this reason, beta positive emitters are moving this way towards the zone of stability. Beta negative emitters, though, they come with a configuration of 0, -1. That means that the daughter atom is going to have more protons. So it's going to be moving this way in order to get to the zone of stability. We have alpha emitters. These are emitting alpha particles with a 4-2 configuration, meaning it is both dropping by 2 protons and by 2 neutrons. So alpha emitters are kind of going like this in order to get to the zone of stability. You'll notice that gamma is not showing up here. That's because gamma's configuration is 0, 0. It's neither changing proton number or neutron number. It's simply carrying away energy. So again, radioactivity, all about getting to that more stable isotope. Next up, we're going to be talking about the effects of radioactivity on humans, and we're going to start by just talking about the quantity of radiation. You may have heard that bananas are actually radioactive. It's because of the potassium that's found in bananas. And so what I like to do when we're talking about how much radiation is I like to use the unit of bananas. Now, don't get me wrong, the IB is not going to give you number of bananas on the exam. And if you go to a nuclear physicist, they're not really going to know too much what you're talking about. But I like to start here because 1 banana, we know what that's like. We know what that exposure to radiation is like. We know that it's not something to be worried about. But you may have heard that X-rays will cause, radiation. It'll expose you to radiation. For example, a dental X-ray is like being exposed to 50 bananas worth of radiation. A chest X-ray, 200 bananas worth. You can see that the release from a nuclear power plant is about 300 bananas worth of radioactivity per year. Simply taking a flight, being high up, is going to give you some radioactive particles coming from down in our atmosphere. So if you fly from London to New York, that's about 400 bananas worth. 2 weeks after the Fukushima accident, the total dose received about 2 weeks after in the town hall was about 1,000 bananas. A mammogram, about 4,000 bananas. 10 years of normal background dose, about 85% of which comes from natural sources, is like 40,000 bananas worth of radiation. A chest CT or CAT scan, 70,000 bananas worth. The maximum yearly dose for a U.S. radiation worker is 500,000 bananas worth. For perspective, if you piled up 20 million bananas, you could get some severe radiation poisoning, fatal in some cases. 80 million bananas worth of radiation is definitely fatal. And whoa, 10 minutes next to the Chernobyl reactor core, right after it exploded, was 500 million bananas worth. Okay, so this gives us an idea because we're familiar with bananas. What we're probably less familiar with are millisieverts. This is a really common unit when it comes to radiation. And you can see, converted over to millisieverts, exactly how many millisieverts per year in some cases correspond to different incidents. For example, we see our dental X-ray down here, 0.01 millisievert. And remember, that's about 50 bananas worth, to give you an idea of what a millisievert is. So looking at short-term dosage, that's emergency status, 500 millisieverts, vomiting and hair loss within 2 to 3 weeks, you can really get into some very, very dangerous zones. So far we've really looked at the quantity of radiation, but we also need to be very concerned with, well, how easy is it to just store it up and make it safe? And this starts to differ based on alpha, beta, or gamma particles. Alpha particles can pretty easily be stopped, like with a piece of paper. So if you had an alpha particle in your pocket, it really wouldn't be a big deal. Beta particles, though, they can go through thin layers of paper, but they are often stopped by like aluminum foil. So if you have some sheets of aluminum, you can stop beta particles. You can safely contain them. The stuff that really is hard to contain are gamma particles, those photons. They can go through like a lot. And the highest energy photons, honestly, you're not going to contain them. The medium energy ones, if you have a thick lead box, you can start to contain it. But our gamma rays are going to penetrate the most. Now, with that in mind, you might be like, oh, I should never be worried about alpha particles, and I'm somewhat worried about beta particles. But think about how you can be exposed. Yes, this is like external exposure if you are standing next to it. But remember that you can also have internal exposure. For example, one of the reasons that made Chernobyl and Fukushima so devastating is because alpha particles got into the air and into the water. And then us humans inhaled the air. We drank the water, and now those alpha particles are inside our bodies. It doesn't matter if we weren't standing right next to it or if there was a sheet of paper between us and the reactor, because they ended up in our bodies nonetheless. So kind of the final question here about like how scared should you be about each of these comes with looking at the ionization that each type of radioactive particle can wreak havoc on your body. So when I say ionization, it means it's going in, it's finding cells, it's mutating the cells in your body. This could look like, in the long term, getting eye cataracts. This could mean, in the long term, lung cancer, breast cancer, skin cancer. This is particularly damaging for reproductive systems in both men and women, especially pregnant women. This could cause leukemia. This could get into your blood, making you more susceptible to other diseases. This could make you vomit, have nausea, some really, really horrible things that this radiation can do to your body. Even the moderate symptoms like fever, hair loss, vomiting, diarrhea, still not fun. If we look at how ionizing, how dangerous each type of particle is, alpha particles are highly ionizing. Sure, you can stop them with a piece of paper, but if you drink some of these particles, if you inhale them, they will wreak havoc on your body. Beta particles are the next in line. They're moderately highly ionizing. And lucky for us, gamma, the ones that are really hard to contain, tend to be pretty poor ionizers. Now remember though, gamma rays often come in conjunction with an alpha or beta decay, and so you might be getting two of these types at once. So to sum up, we have alpha, beta, and gamma decay, beta negative and beta positive. We've looked at the type of particle that's being expelled from the nucleus in order to achieve stability. We've recognized that some of these reactions come along with these mysterious neutrino stuff we'll learn more about soon. We've looked at how easy it is for these particles to penetrate, meaning like what would we need to do to truly store them? And we've looked at the ionizing ability of each particle, meaning how dangerous are they for our body? So the last part of this lecture, I want to focus on how long does a substance actually remain radioactive? And for this, I'm going to head over to PhET, Radioactive Dating Game. So I have this set right now to look at uranium-238, these kind of little gold particles here. Uranium-238, of course, used in nuclear fission. This is an unstable nuclei, and so it's going to want to undergo radioactive decay in order to become lead-206, a more stable isotope. So let's take a look. I want you to particularly look up here once I add all of our nuclei. Add that in, there we go. And then I also want you to notice As these gold uranium change into gray lead, you're going to see a gold line being plotted here and a gray line being plotted here. Let's take a look. And here we've reached about halfway, 4 billion years in, we're about halfway transitioning from uranium to lead. Approaching 8 billion years, we're just about at a quarter. And if we let this run long enough, indeed, all of those uranium particles will end up decaying into lead particles. Now, you see that there is something called half-life right here. I would say that one half-life, this red dotted line, corresponds to when our original uranium-238 radioactive substance has decayed by half, down to 50%. Let's take a look at with this in terms of carbon-14. You might have heard of carbon-14 used in carbon dating. Let's take another look. Reaching the half-life right now. Reaching its second half-life, so 25%. Reaching its third half-life, 12.5%, and so on. So let's take a moment to define half-life. Half-life is going to be the time taken for the radioactivity of a specified isotope to fall to half its original value. And this is why we call it half-life. Each time is going to get halved and halved and halved. So what you were seeing in the PhET was a graph, something like this, number of half-lives, or sometimes we simply put time in order to see that half-life, on the x-axis, and the percent of the remaining parent isotope on the y-axis. The first half-life reduces 100% down to 50%. And then you're reduced again by half down to 25%, and again by half down to 12.5%, and again by half down to 6.25%, and so on. And so you could imagine if you had a half-life graph for any particular substance that you're worried about, that you want to store, and you had a threshold of, oh, when it gets below 5% of radioactivity, it's considered safe for humans, or whatever that threshold is set by, the government. You could start to figure out how long would I need to store this radioactive substance until it fell below that safe amount. So half-lives can be really important, determining how long we have to be worried about that radioactivity. Okay, let's take a look at our gear up problem. So this question is going to be about radioactivity, obviously. Cesium-137 is a radioactive waste product with a half-life of 30 years that's formed during the fission of uranium. Cesium-137 decays by emitting beta- or beta-negative particles to form a nuclide of barium-137. State the nuclear equation for this reaction. Determine the fraction of cesium-137 that will have decayed after 120 years. And explain, with reference to the biological effects of ionizing radiation, why it's important to be shielded from radiation emitted by cesium-137. Pause the video here and try this problem. Okay, here is our nuclear reaction. We have cesium decaying into barium, beta negative, and an anti-electron neutrino coming along for the ride. Neutrinos and anti-neutrinos come along with a 0-0 configuration. Again, we will learn more why that neutrino is there in a few days. Do a quick check. We should have conservation of mass. Our top numbers should all be conserved as they are. And conservation of charge, making sure our bottom numbers are conserved, and they are. For part B, determining the fraction of cesium that is going to have been decayed after 120 years. I'm going to take that 120 years and I'm going to divide it by the 30-year half-life that we were given in this problem. This tells me that there have been 4 half-lives that pass. So 4 30-year periods that will pass. So I'm going to think through this. I started with 100% of my radioactive substance, and after the first half-life, I've decayed to 50% of my radioactive substance. After the second half-life, I'm at 25%. After the third half-life, I'm at 12.5%. And after my fourth half-life, I'm at 6.25%. So whatever that initial amount of radioactivity that I had, I am now down to just 6.25% after 4 half-lives. And last but not least, explaining why this beta decay would be really important to be shielded from. You could have discussed things like the short-term effects, such as your skin being burned or being all red. You could talk about the long-term effects, like genetic disorders, like cancer. It would be very important to store this because beta particles have kind of a medium penetration level. So you would want to store this in some sort of like thick aluminum box. And of course, it's important to store these because they have, beta particles have medium ionization, meaning that they can ionize the cells in your body more than gamma particles, but less than alpha particles. Okay, so to wrap up today's lecture, we have talked about the properties of alpha, beta, and gamma radiation, including those neutrinos and antineutrinos that come along for the ride with beta decay. We've talked about the biological effects, what it can do to your body, and the ionizing properties. We've talked about the cause of this decay, being trying to get to that more stable nuclei. We know that this decay is going to be a random process that spontaneously happens and on average will correspond to that half-life. And the half-life being that decay curve, we can use that to solve problems about how much of our radioactive substance will be remaining after a certain amount of half-lives.